Okay, so let's wrap up the section on scalar fields. This is the last chapter on solutions, on Friedmann solutions I'm doing. I'm afraid I have to write the two basic equations again. So first Friedmann equation, come on. With scalar field source. And I restrict here to the case k equals 0 and lambda equals 0, because the action of the scalar fields we want to discuss are relevant in particular or more or less only in this case. So the first Friedmann equation was this here. This is a Hubble parameter squared 3 times. And on the other side, the k term is not there, it's 0, and the lambda term is also 0. And on the right-hand side, we have the energy density produced by the scalar field phi squared plus v of phi. So our scalar field has a certain potential, phi, v of phi, and the only standing assumptions we are making is that it should have a strict minimum somewhere, which is an absolute minimum. So it should have a vacuum state, a ground state, which I denote v phi v. It may have additional extrema, and actually we will need additional extrema for what I'm doing today. So that's the first Friedmann equation, and then we have the Klein-Gordon equation, the generalized Klein-Gordon equation on a Robertson-Walker universe. This is 1 over c squared. Second derivative of the phi field plus, again, the Hubble constant or Hubble function, 1 over a dA by dt. Yeah, that's a Hubble function times d phi by dt plus the potential primed derivative of the potential. And I've already emphasized that this equation looks like an equation for a particle in classical mechanics. Yeah? So here you have the acceleration. Here you have the driving force. The force is produced by a potential. And here you have something like a damping term. Yeah, and the damping is governed by the Hubble function. So you may imagine your scalar field as in particular, the inflation theorist used to say that the field is rolling in this potential. Yeah? It's a second order equation. So you may give initial conditions for phi and for the derivative. So you put it somewhere and you shove it a little bit. Yeah, you nudge it a little bit. And then it's moving in this potential with a damping term. Yeah, so you may, the inflation theorists used to say it's rolling in the potential. Actually, it's not like an extended particle which is really rolling. It is, I would prefer to say it is sliding, but the standard terminology is to say it is rolling. So I would say it is sliding with a friction term. Yeah? So if you set it here and nudge it a little bit, then it will oscillate and it will settle down because of the damping term, provided that the Hubble function is positive. If the Hubble function is negative, it would have the additional effect, negative damping. Okay, and what I demonstrated last time, the last thing I did, which is crucial for everything I want to say about the scalar field case, is that it can mimic a gravitational constant with this theory. So we set the gravitational constant equal to 0. It's not in the game. But nonetheless, we can produce effects which are exactly the same mathematically as what a cosmological constant would do. And in order to do this, we have to choose the phi field as constant. And of course, because of the second equation, this only, if it is constant and this is 0, so it only works if it is an extremum. Yeah? So of course, we must have v prime of phi naught is 0. So we have it either here in the ground state, or in some other minimum, or maybe also in a maximum or in a saddle. Yeah? Just the first derivative must vanish. And we can see what the equations then do. Then the equations do the following. We have done this last time already, but I need it on the board because I want to continue now with this. If I look at the first, this Friedmann equation, then I have 3 over a squared dA by dt squared is kappa c. Is it not c? It's c squared, of course. Oops, c squared. And there's also here a factor c squared. That's yes, that's it. So there's kappa c squared, and then this is constant v of phi naught. It may be 0. Yeah, if we are in the ground state, then the right-hand side is 0. If we are not in the ground state, then the right-hand side is non-zero. And we will see that actually the exponential growth, which we want to produce, which mimics the cosmological constant, needs another extremum. It is not allowed to be the ground state. Well, if it is a ground state, if this is 0, we see this is not 0, of course, that the derivative of A must be 0, so A must be constant. A constant is not the effect of a cosmological constant. This gives Minkowski space because we have k equals 0. Yeah? So we don't want to have Minkowski space, so we don't want to have this different. Yes, the derivative is 0, but we want to have the value of the field different from 0. And actually, because we have it bounded by 0, it must then be strictly positive. And this can be integrated. I did this already last time. It's 1 over a dA by dt is plus or minus kappa third. Oh, let me put the c first, and then the square root of kappa over 3 v of phi naught. And that's easily integrated. That gives the log, right? So it's L m a over an integration constant a naught is e to the plus minus nonsense. It's just plus minus c root kappa over 3 times t. That's the solution. We can solve for a. And then we see it's the effect of a cosmological constant. It's exponential growth. So we have a of t is a constant a naught. And now comes the exponential plus minus c root kappa over 3 v of phi naught t. We are free to choose the integration constant as we like, and also the sign. We can have exponential growth or exponential decay, depending on whether we want to reproduce the upper half of the upper right-hand half of the de Sitter hyperboloid or the lower left-hand half. So we choose plus sign because we want to have an expanding universe, and we choose a naught as an inverse of this. Look, c times t, what is that? C times t is a length. So this must be an inverse length. So a naught is also a length. So we could choose it as the inverse of this here. Root over 3 kappa v of phi naught. And this is not 0, so I may write it in the denominator. And then we have a of t is root of 3 kappa y of phi naught e to the plus c root kappa over 3 of phi naught t. And that's precisely the de Sitter universe. Yeah? K equals 0, de Sitter universe with flat slicing. This is precisely the scale factor of the de Sitter universe with flat slicing. If I slice the upper right-hand part under 45 degrees into flat spaces. Yeah, so the picture is this here. We only consider the upper right-hand, should be tangent to this, sorry. Oops. Yeah, so this is not there. This is not covered by this Robertson-Walker space-time. So we cut this under 45 degrees. And remember, we have this funny Minkowski metric, not the Euclidean metric, on the hyperboloid. Yeah? And because of this, what we get here are really flat Euclidean spaces. Yeah? If you look at it with your Euclidean eyes, of course, you will say, hey, wait a minute, this is curved, right? It comes down here and then it goes up on the other side. That's not flat. But actually, if you use the induced metric, which comes from the 5-dimensional Minkowski metric, then they really come out as 3-dimensional Euclidean spaces, flat positive definite spaces. So this is de Sitter with flat slicing. Yeah, and well, when we encountered the de Sitter universe for the first time, we said it was a solution with a cosmological constant. And now we say, no, we don't have a cosmological constant, we have this funny scalar field. But it acts like a cosmological constant. And the analogy is, acts like a cosmological constant. So what do we have to identify with lambda? Oops. So the lambda corresponds to what, if you remember? Well, this here is, I said it's a length. Yeah? The cosmological constant has dimension 1 over length squared. So this must be, the cosmological constant must be kappa times v phi naught, right? Kappa times v phi naught. So the bigger you make this difference, if this here is your phi naught, then this here is v of phi naught, right? So the bigger you make this, potential, the difference of the extremum where you are to the vacuum state, which by our choice is at the level v equals 0. The bigger you make this thing, the bigger is the cosmological constant you are mimicking. And you can do this now to mimic the cosmological constant which we need for the accelerated expansion now, which has a fairly small value. Yeah? So in conventional units, if you give it in, that's 1 over meter squared, right? 1 over meter squared. In this unit, it's something like 10 to the minus 22. Yeah? So it is a very small number which we need for the expansion which we observe right now, the accelerated expansion which we need right now. And yeah, if it is really precisely in an extremum, actually it need not be a minimum, could also be a maximum and a saddle, but a minimum has the advantage that it is stable at least with respect to small perturbations, right? So if you set it in this minimum and now we perturb it a little bit, then it will oscillate around this. If you put it in a maximum, if you don't breathe, it will stay put. But as soon as you touch it a little bit, it will go away either in this direction or in this direction. Yeah? So this would be unstable, this would be stable. If you want to have it stable, then it should be a minimum. So your potential should have a second minimum. Then you could mimic a cosmological constant which is stable at least over a certain while. And if you mimic the cosmological constant which produces the accelerated universe we need now, for the observation now, then you call this scalar field quintessence. Yeah? Quintessence is a reinterpretation of the cosmological constant put to the right-hand side and then interpreted as a scalar field source. And this scalar field is called the quintessence field. So if you choose the value of lambda chosen for producing accelerated expansion now, then you call phi the quintessence field. Of course, this reinterpretation has the advantage that it's not necessarily precisely constant, right? If it is really a cosmological constant, then it's constant. That's why it's called cosmological constant. If we say it is actually a scalar field, which is sitting in a minimum, then we may think about the possibility that maybe it's not forever in this minimum. And maybe it's not even precisely stable in this minimum. Maybe it oscillates a little bit around this. And in this sense, one often says that this quintessence interpretation makes the cosmological constant dynamic. Yeah, it can now depend on time. And then we don't know what happens in the future, right? If it's really a cosmological constant, then we know that asymptotically it must become de Sitter, whatever else there is on our space-time. Because in the end, the cosmological constant term always wins. Yeah, all the matter-filled universes, which we have discussed, asymptotically go to de Sitter if there's a positive cosmological constant. So if there's a dust or if radiation or whatever, it dies away in comparison to the cosmological constant for large time. But if it is made dynamic, then maybe it starts doing funny things in the future, and then it's not necessarily expanding forever. So if you reinterpret this term as a quintessence field, then you cannot say anything about the future of our universe. Yeah, but it's a strict cosmological constant, then our universe will expand forever. There's a question?
Yes, does one know what may produce such large oscillations in a minimum so that it can spin?
Well, there are other fields on the space-time. So the scalar field is not alone in the world, actually. Yeah, over a certain period, it may be dominating, but there are also other fields, and it may interact with this field. It also, that's something which we will discuss fairly soon. This idea that we are in a strictly homogeneous and isotropic universe is, of course, only an approximation. Actually, there's also a dependence on the space coordinates of the phi. And we will discuss what they are doing. Yeah, of course, they also bring in some new ideas. We will see that actually they will never dominate under the assumptions we are making. So they are neglected. They are neglectable under fairly general assumptions. This means the idea of a homogeneous and isotropic universe is not so bad. But actually, they are there. They are not precisely zero. They may be small, but they are not precisely zero. And for this reason, it's not clear that the field actually stays in a minimum when it starts in a minimum. Okay, so this was one possibility to interpret a scalar field with its properties as producing the acceleration we need now, yeah, to fit the observations which we do right now. The other thing, which is even more important, is that we want to produce an accelerated, actually exponentially growing expansion in the very early universe. That's what we call inflation. This does not work with the cosmological constant. So if you want to mimic if you introduce a quintessence field, actually the quintessence field to what we know by now could very well be precisely constant. There's no need, no strict need to make it dynamic. So we could leave it on the left-hand side and say it's a cosmological constant. Would be in agreement with all observations until now. It's different with the inflation. Inflation, if it's really a true cosmological constant, if it had produced this enormous growth in the beginning of the universe, it would produce an even more enormous growth right now. And that's not what we observe. So the inflaton field should switch itself off. That's what one calls a graceful exit. And a cosmological constant never switches itself off. So for the inflaton, we really need a potential. And so this was the first thing. And now lambda chosen for producing inflation, then it cannot be strictly constant, and then it's called then phi is called the inflaton field, and lambda must be enormously much bigger than for this case. Yeah. So as I said, in conventional units this is small, but in conventional units this is huge because it produces this enormous exponential growth in a very short period at the very early universe. I already told you that the time scale over which this happens is something like 10 to the minus 30 seconds, 30 something, 35, 36 or something like that. So it's really an incredibly short time at the very, very early universe. And this does not work with a precisely constant field. So this setting here just mimics a cosmological constant precisely. This does not give us inflation. It would give us an exponential growth which goes on forever. So we have to choose the phi not exactly constant. Yeah, because it should switch itself off. And if it is constant, then it never switches it. It switches itself off. Exactly constant, but as one says, slowly rolling. Yeah, so it's not precisely constant, just sitting there. It's slowly rolling in the potential. And a typical potential which gives inflation is something like that. If you have phi, v of phi, you have a plateau where the potential is not exactly constant. Let's say it begins with the value of phi naught, and here is v of phi naught. But actually, this is not precisely an extremum. So the field is actually very slowly rolling down this slope. And then we need a graceful exit, and the graceful exit happens when it has arrived in the true vacuum state. So if we are in the true vacuum state, I said if I do this game here, not with v of phi naught bigger than 0, but rather with this v phi, where the v is 0. Then I have the 0 here. I have the 0 in the exponent. This means A is constant. Yeah? So there's no exponential growth. So if this situation is reached, then actually the scale factor will, as far as the influence of the scalar field is concerned, it would stay constant. And then the other contributions from the matter and from the radiation could take over. So that's the idea how inflation could be produced. So as long as the particle is, or the field is rolling down the slope, we have almost this situation which we were covering before. So here we have, that's the inflationary period. So it's not precisely exponential growth, but approximately exponential growth. And actually you can make the factor by which the exponential growth takes place. You can make it arbitrarily big by making the difference of the potential here and the potential in the vacuum state, which is 0 by our convention. If you make this arbitrarily big, yeah, you can make this factor arbitrarily big by making this height arbitrarily large. And actually we will discuss how big it must be in order to fit the observations. So as long as the particle or the field rolls down this slope, we have almost exponential growth. But then, you see, now it's no longer constant. Yeah? Now the change of the potential becomes considerable. This means the growth is no longer exponential. And actually, think of the analogy with a particle in a potential with a friction term. The Hubble constant or the Hubble parameter produces friction. Then it will start oscillating here. Yeah, it will overshoot a little bit, then it will turn back, it will start oscillating, 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 and because of the damping term, it will settle in V phi. So this here is a graceful exit. So we have an exponential growth in the inflationary period. So if I plot the scale factor over t, we have this enormous exponential growth over a certain period. Well, yeah, don't confuse the two things, as the phi is almost constant in this period, and the scale factor grows up dramatically. Yeah? So the two things are not synchronized, so to speak. Yeah? The A is almost, the A is growing dramatically, and the phi is almost constant, and then we have the graceful exit. So this is inflation, and this is the graceful exit. So that's the inflationary scenario. So if you believe in the existence of such a field with such a potential, then you can produce this exponential growth which you want to have in order to solve these three problems which I had mentioned last week. So as you see, recall this comparison I've mentioned, which Rocky Kolb always makes with the duct tape and the cars. Yeah? You see it here very clearly. Yeah? You invent something, you invent this scalar field, just in a way that everything works the way you want to have it. You don't tell where the field comes from, what the field is, or what the really fundamental underlying law is. You just introduce it by hand to solve a problem which you want to solve. So in this sense, this is not a satisfactory state until now. And what the inflaton actually is, if one can explain it from a more fundamental level, this is a matter of debate. Actually, when Guth invented inflation in 1980, he identified it with the Higgs field. Yeah? And maybe those of you who are familiar with the Higgs mechanism, maybe they have already realized that the shape of the potential reminds a little bit of the Higgs potential. Well, there's one difference. I have considered the inflaton here as a real field. And that's what one usually does. It's not necessary to make it complex. The Higgs field, of course, is complex. It must be complex. Yeah? So it's a complex valued field. So the potential is actually not a potential over a line. It's a potential over a complex plane. Yeah? So you should consider the whole picture which I'm drawing now to be rotationally symmetric, so that you are not over the real line, but rather over the complex plane. But nonetheless, I draw just the cross-section. So phi is now, this takes now values in C. So think of that as being the complex plane. Yes, the whole thing is rotationally symmetric around this axis here. And then the Higgs potential, that's the famous Mexican hat potential, right? So it looks like a sombrero, a Mexican hat, yeah? And what the Higgs field does is it starts here in the so-called false vacuum. And this is the true vacuum. So if it starts here, that's an unstable equilibrium. So as long as you don't breathe, it will stay there. But if you perturb the system a little bit, then it will roll down this slope. And because the whole thing is now spherically symmetric, rotationally symmetric around this axis, it has now a choice into which point in this circle it will actually roll down. Yeah? And that's what one calls spontaneous symmetry breaking. Because this thing is symmetric around this axis. It's rotationally symmetric. If it has settled down in one point in this circle, then it has broken the symmetry. That's what one calls spontaneous symmetry breaking. And this rolling down, this difference here, this difference in potential heights, this gives the mass to the particles. Yeah? This is a term which gives the mass to the particles to which the Higgs couples. So it's quite analogous to this here. So the idea to identify the two things is quite natural. And after Guth, many other people have also tried to identify the two things. Actually, until now, the theory doesn't really work. So the inflaton must have other properties than the Higgs, as far as we know it by now. So there's no unified theory for the Higgs and the inflaton until now. And there's also no unified theory for the inflaton and the quintessence field until now. You might think maybe that's also the same thing, right? Actually, that's even more natural to think. So you have in the period when let me show it here. When the inflation takes place, the particle rolls down here, and maybe this is not the true minimum. It's only a metastable state, so it can roll over a maximum and then settle down in another minimum. You might think of something like that. So then you have inflation, graceful exit, but not precisely with v equals 0. It's actually not the true vacuum state, and then it overshoots and settles down in another minimum, which gives the gravitational constant now. Would be possible. Yeah. Of course, where the drawing is very bad, because it's not too bad. Actually, this height should be much bigger than the height where the final where the final minimum is. Yeah. Because the cosmological constant which you need for inflation is much bigger than the cosmological constant you need for quintessence. So also this has been tried, of course. But again, there's no really successful theory which unifies the two concepts. And yeah, what if these fields, or in the quantized version, these particles can be interpreted in a microscopic way? That's also a question which is completely, in a fundamental microscopic way, really in terms of our elementary particles. That's also a completely open question. So at the moment, they are just introduced by hand, these fields. One sees it works, they do what they want to do, what they should do, but we don't really know where they are coming from. And I really want to emphasize that inflation is not a fully established theory which is beyond any doubt. Inflation is still something at a speculative level. I think it's fair to say that the vast majority of cosmologists are fairly convinced that something like inflation has taken place. But it's not yet a well-established and well-understood complete theory. And actually, there are very prominent opponents. Roger Penrose is the most famous one. Yeah, if you have read The Road to Reality, the most recent book of Roger Penrose, there he discusses the notion of inflation rather critically. So he's not convinced that this is a good and reasonable concept. But he's in a minority position, certainly. I should also say, I already mentioned that Guth wanted to interpret what we now call the inflaton with the Higgs field. This scenario which I've presented here is not the scenario which Guth discussed. It's the slow roll inflation was introduced by André Linde and simultaneously by Steinhardt and what's the other name? Albrecht and Steinhardt, a little bit after Guth. But I think it's the easiest way to produce an inflationary scenario. That's why I have discussed this here. So there's a big variety of inflationary scenarios, how you can do it in detail. This idea of a slowly rolling particle in a potential of this shape is, I think, the simplest one. That's what one calls slow roll inflation. Okay, so this gives you the mathematical idea of how inflation can be set into action. And we will now link all these things we have been discussed until now in relation with observations. So this will now be the next chapter. Maybe I should draw a little time scale. I'm not sure if this is the best time to do it, but at some time I should do it. So if we have now learned a lot of things about solutions of Friedmann equations with this kind of matter, with other kinds of matter. And actually, I hope we have everything together which is needed for understanding of our present view of the universe. So we have, at the present period, we have something, we need the cosmological constant. We need the cosmological constant for the accelerated expansion. And we certainly have matter around. And matter is partly luminous matter and partly dark matter. So at the moment, we have lambda plus dark and luminous matter. Yeah. So that's the matter content we need for the universe right now. We need the lambda, or you may write it on the right-hand side and reinterpret it as a quintessence field. But there's nothing wrong with interpreting the present-day observations if you leave it on the left-hand side and say it's just a constant. So that's what we need now. If it's really a strict cosmological constant, then it will take over in the future. Not a good drawing. So it's here expanding in an accelerating way, and then the lambda term takes over. So here we have this period. I need more space. Very bad. So that's this accelerated expansion, and then we have here the lambda alone. If it's really a cosmological constant in the very late universe, the lambda will take over. Then we have talked about the fact that matter will be dominated by radiation at earlier stages. Yeah, because radiation falls off more strongly than matter. Matter means dust. Yeah, it's a dust model. This goes with a to the minus 3, and the radiation term goes with a to the minus 4. We have discussed this. So before this, there's a period where we have radiation, where the radiation is the dominating part. And then we have inflation. Oops, yeah, it goes really down dramatically. And here we have the Big Bang. What exactly is going on here, we don't know. So that's the picture which we should have in mind. That's the scale factor what I've plotted here over T. Yeah? And I hope we have now the mathematics at our disposal to understand all the periods. Yeah? Lambda alone, this would mean for if the matter content has become irrelevant for very late times, if we have the lambda alone, this would mean de Sitter. And that's why I emphasize that de Sitter is an important cosmological solution with a positive lambda, not with a negative lambda. That's anti-de Sitter. This is irrelevant. But with positive lambda, it's very relevant as an asymptotic solution. Here we have this class of solution which unfortunately cannot be it can be written down analytically, the solution, but I haven't done it because it's a little bit awkward. You need these elliptic functions. Yeah? I did this explicitly. This gives a cycloid for k curvature positive. This gives the Einstein de Sitter for k equals 0, and the hyperbolic cycloid for k negative. So this can be done very easily analytically, and we have done this. With the lambda term, we would get elliptic functions and elliptic integrals. And I have discussed this only qualitatively. But that's what we would actually need for our present universe. And the radiation alone we have done explicitly. This gives this, as I said already, the density falls off with a to the minus 4. And right now, I have given you a rough idea of what inflation is about, where the inflaton is the dominating thing. So the exponential factor grew dramatically. And yeah, we believe that there's a hot Big Bang at the beginning, but how exactly this happened and what kind of solution we need in the immediate neighborhood of the hot Big Bang, that actually we don't know. So this is, and certainly some kind of quantum gravity will probably be needed in order to explain this. So that's what one calls the concordance model. And I have just put it here on the board to give you an idea what part of the things we have been discussing in the last weeks will be relevant for this. But of course, I still need a justification why this is a good model for our universe. And the only thing which can give us a justification is observations. And I will now, in the next I think 1.5 weeks or so, I will now discuss observations. Of course, a lot of things, not a lot, but several things I've said already in the brief historic overview, and I will repeat now a couple of things, but we will now discuss it on the basis of our understanding of solving Einstein's field equations for Robertson-Walker universes. Actually, I've realized that I made a mistake with the numbering. So the last section was going under the number 2, but the section before this was also going under the number 2. I should have used LaTeX for the numbering. So actually, what we now do is already section 4. And well, what will I do? What kind of observations do I want to discuss in this section? I will begin with our evidence for dark matter. So why is it not sufficient to consider here the ordinary luminous matter? Why do we need dark matter? What kind of observational evidence do we have for the existence of dark matter? This will be the first subsection. Then I will speak about the Hubble law, the distance redshift relation. This will introduce the need for this term, which you may call dark energy, or which you may call a quintessence, or whatever you like, or a cosmological constant. Essentially, it's different names for the same thing. Then, of course, I will talk, this will be the longest subsection about the cosmic microwave background radiation. And I will give you an overview of what importance lensing observations have for the cosmology. So these will be the 4 subsections I'm doing. For me, I'm also saying a few words about number counts. I'm not yet sure about that. I've thought for quite some time how to arrange these sections. Actually, it would be necessary to do all of them simultaneously, but that's not easily possible. So I have to order it in a certain way. So I begin with evidence for dark matter. Evidence for dark matter. In this section, I will already have to talk a little bit about lensing. Then I will come back to lensing later, so it's a little bit jumping forward and backward, but I think that's unavoidable because the things are interrelated. So why are we convinced that a part, and actually a fairly large part of our universe, exists in the form of dark matter? Dark matter is an old concept. Yeah, it's much older than dark energy. Dark energy is new. It was introduced a little bit more than that, 17 years ago or something like that. Roughly 20 years ago, but not more than that. Dark matter is much older. Dark matter was introduced in the 1930s already by Fritz Zwicky. So the first evidence for dark matter was the velocity distribution in galaxy clusters. Not in galaxies, but in galaxy clusters. And this was done, as I said already, by Fritz Zwicky. These are 2 papers. The first was from 1933, and the second from 1937. And the first one is in German. And in this paper, he really uses this word dark matter. Dunkle Materie. Dunkle, kalte Materie. It's literally in this paper. Yeah, so what we now call cold dark matter. This was predicted in this 1933 paper. And why did Zwicky, what brought Zwicky to think that there must be a lot of matter in the form of dark matter, which we don't see? Well, what he investigated was the velocity distribution in a particular galaxy cluster, which is called the Coma cluster. Yeah. This is a constellation where this cluster is in the sky. So that's the constellation Coma Berenices, which is now in the springtime, which is high in the sky. So you can see it nicely in the evening. So what you see there is a galaxy cluster, something like 1,000 galaxies, already at this time in the 1930s. So Zwicky had already something like 1,000 galaxies available. So he had observations on them. He had the redshifts, which gave him the radial velocities. And from the radial velocities, he estimated how much matter would be necessary in order to bind these galaxies. The idea is that all these galaxies in the galaxy cluster are gravitationally bound. And now, if you look at one particular galaxy, if you look at the velocity of this, then it should be on an orbit around the mass, which is the mass of all the other ones. And if it's really gravitationally bound, then it should be in a way that it is on a more or less stable orbit around these other masses. And well, this is a Newtonian problem. Yeah, so the galaxies are so far apart, you don't need relativity. Yeah, so the distances between them is very, very big in comparison to the Schwarzschild radius. Has nothing to do with general relativity. It's just Newtonian theory. And what Zwicky estimated was what kind of mass would be necessary in order to keep the galaxies moving in the way as it was observed. And he found that much more mass was necessary than what was actually visible. Yeah? So on the one hand, he had the motion of the galaxies, the radial velocities at least. So he could estimate which mass was necessary to keep this thing together, this coma cluster. And on the other hand, he saw the light coming from the galaxy, which allowed him to estimate the total mass of the luminous matter in this galaxy cluster. And he found an enormous difference. Actually, he found a factor of 500. Yeah? So he said that one needs 500 times as much mass as one actually sees in order to explain that the coma cluster is gravitationally bound. And actually, this number was wrong. Today, we don't believe that it is that big. The reason was that he dramatically underestimated the distance of the coma cluster. And our distance scale has changed in the course of time. There was a mistake in early years. So in order to estimate the distance of something, Hubble and other people use the so-called Cepheids, a kind of variable stars, where the period is related to the true intensity, to the true luminosity. And they were used as standard candles. And they were wrongly calibrated for several decades. Actually, this was realized in the 50s, that there was a wrong calibration. And in the 50s, all the distances dramatically grew. Yeah? At the same time, the Hubble constant dropped. Hubble believed in a Hubble constant of something like 500. Kilometer per second per megaparsec. Yeah? Today we have a value around 70. Yeah, so it really dropped dramatically. And at that time, the distances were dramatically underestimated. So Zwicky thought that the coma cluster would be away something like 10 megaparsecs, 10 or 15 megaparsecs. Actually, it's more than 100 megaparsecs. And that's what gave him the wrong number. So what he observed was that velocity distribution is explainable for a bound system, gravitationally bound system, only if the mass is, as he said, about 500 times. What is this? Let me write it in a different way. So then the other part is 1 over 500. That's 0.2%. Is that true? 0.2%, right? So 99.8% would actually be dark. Yeah. If I do this calculation correctly in the hand, if the total mass of the cluster is to something like 89.2% dark. And as I said, we don't believe in this number anymore. The analysis Zwicky did was correct, was absolutely correct, but he just had the wrong number for the Hubble constant, for estimating the distance. And today we believe that it's something like 95%, yeah, which is already fairly big. Yeah? So this was the first evidence for the existence of dark matter. And I said he really used the word dunkle Materie in this paper, in this 33 paper. In the 37 paper, actually the detailed analysis of the dynamic of the coma clusters in the 37 paper, which is in English. And I think it doesn't contain the word dark matter. I'm not quite sure. But as far as I remember, he just analyzes that, there's a missing mass. But this earlier paper, this really uses the word dunkle Materie. And actually, Zwicky was great in introducing terminology. Yeah? He also invented the term supernova. Yeah? Nova, of course, is a very old word. It was used already in the Renaissance, Kepler and so on. They spoke about novae I think is the English word. So when a star was seen in the sky which hadn't been seen before, they called it a nova. And of course nowadays we know that this is not a star which is newly born, but rather a star which is exploding and then becomes much brighter than it was before. But the mechanism of a supernova, and also the word supernova, was introduced by Zwicky. Zwicky was also a pioneer of the idea of neutron stars. Together with Bader, he wrote actually the first fundamental paper on neutron stars. And he was a pioneer of gravitational lensing. He was the first who actually looked in the sky for double images, for lensed images. So he was really a very thoughtful and very innovative astronomer. He's also infamous for having been a rather rude person. I don't know if you have heard these stories that he used to address people as spherical bastards. He is famous for that. Yeah, by that he meant that from every direction you look at them, it's always a bastard. And he could be really rude to persons. There are many stories about it. Although I also met a couple of persons who met Zwicky and who said that actually he could also be very charming. And it was actually many stories are maybe a little bit overdone. Okay, this was Zwicky's contribution. So he's the father of dark matter. So at that time, of course, it was completely open what the dark matter is. It was just the first hint that something like that should exist. I need something in the galaxy clusters in order to explain that they are gravitationally bound. At that time, this wasn't really taken seriously. So not many, almost nobody, actually followed up on this idea. So it was there since 1933 in a paper, but nobody discussed it seriously as far as I know. So it became a matter of the general community in the 1970s. So in the 1970s, the rotation curve of galaxies were investigated with an incredible stamina by a lady with the name of Vera Rubin. And some of the work was done with a collaborator by the name of Ford. Did I note the first name? No, here I just wrote Rubin and Ford. Sorry, I don't know what the first name of this gentleman is. So this was, say in the period between 70 and 80. Already began in the late 60s, I think. So what did Mrs. Rubin do? She observed galaxies in the sky, spiral galaxies, which we observe almost edge-on. Yeah? So we look at the galaxy so that we see the disk almost edge-on. And then, of course, the spiral galaxies are rotating. This means one half comes towards us. So here's a disk. There's usually around the center something which is called the bulge. So something like that, that's a very rough picture of a spiral galaxy seen edge-on. And because the thing rotates, this moves away from us, and this comes towards us, or the other way around. Yeah? And this can be seen in the spectrum, of course. Yeah? So you see there's a Doppler effect. It's quite just the ordinary Doppler effect. Has nothing to do with cosmological redshift, just the ordinary Doppler effect which comes from the relative motion. That one part is redshifted, the one which is moving away from us, and the other part is seen blue shifted on the other side. And this can be done now for different parts here, independent of the radius. So Mrs. Rubin directed her spectroscopic apparatus to different radii here, and then she plotted over the radius for many galaxies. She had a big sample of spiral galaxies over all these years. She plotted this is the radius, and this is the radial velocity, which follows via the Doppler effect from the seen spectral shift. Yeah, the spectral shift gives the radial velocity. And well, what would you expect? Well, in Zero's approximation, you may assume that that's a very bad approximation, but not totally idiotic, that the whole mass of the galaxy is concentrated in the center. Yeah? At the Zero's approximation, you may assume this. Then you have just the Newtonian 1/r potential. And now if you remember, balance of gravitational attraction and centrifugal force, you get a 1/√r curve. Yeah, so this is proportional to 1 over root of r. So this would be for it's a little v, it's a velocity, yeah? Radial velocity. This would be in a potential, in a 1 over r potential, just Newtonian theory. Now, of course, the total mass isn't completely concentrated in the center, so that's only, as I said, a very rough approximation. If you take the extension of the mass into account and also the influence of the disk, you get something which is regular at the center. There's not the singularity which the 1 over r potential of a mass point would produce. It isn't a mass point, it's a regular distribution. So it should start with a regular thing and then being approximated by this fall off. That's what you expect. So this is what you expect. So this is a rotation curve which one would expect on the basis of our gravitational theory. But that's not what one observes. What one observes is actually that this stays. So if one makes a model where you have a central region with a bulge, this so-called bulge here, and you have the influence of the disk, of the spiral arcs, as we see them in the sky, yeah, from the visible matter. That actually the curves in the beginning they were similar like that, but then they stayed. They didn't go down. They even went slowly upwards. So that's what she observed, and not just for one galaxy, but for a large sample of galaxies. So what's the interpretation? The interpretation is in a region where we don't see anything. Here in this region, there must be matter, yeah, which keeps this curve up. Yeah? There's not this fall off which the ordinary, the Kepler orbits would give in this potential of the mass of the visible masses, in the potential of the visible masses. So there must be something like so the explanation is there is a dark matter halo. Around the galaxy. Each of the observed galaxies. And actually, this must be a considerable portion of the total mass of the galaxy. Actually, in the first papers of Rubin, she estimated that it must be about 50%. Yeah? In the first papers, you find this number, explanation. So Rubin, at least 50% of the total mass must be dark. This was underestimated. Yeah? So Zwicky, to a certain extent, overestimated the contribution by dark matter in the clusters. Rubin underestimated it in the galaxies, so that today accepted value is something like 85%. Maybe a little bit more, 85, 87, something like that. That's the numbers you usually find nowadays in order to explain the observation, in order to explain these rotation curves. And this was taken seriously. Yeah, as I said, Zwicky was largely forgotten, so almost nobody quoted this paper, these papers on this idea of dark matter in the years after it has appeared. But this was really a revolution. Yeah, so this was immediately recognized by the whole community that this is a very important observation, and it changes our view of the universe dramatically. And then, of course, people also remembered, Zwicky had already done this many decades before. And now this paper also has a lot of quotations, of course. And when dark matter is mentioned, Zwicky is always mentioned as a father of this idea. So that's just an observational fact. So if you believe in the ordinary gravitational theory, so you say, I don't want to modify the gravitational theory. So it's at this level, it is just Newtonian gravity. Yeah? So there's no difference. If you calculate these rotation curves with general relativity or if you do it just with Newton, there's no difference. Because you are so far away from the center that the distance is much, much bigger than the Schwarzschild radius of the masses. So general relativity plays no role for this. And if you stick to this theory, so general relativity and Newton as an approximation, then you have to postulate that there is this matter, this dark matter. The question is, what is it? Yeah, the question is, what is it? And there are many ideas about this, but before doing this, maybe I should tell you what the profile of the dark matter is, which you need in order to explain the observations. So I said you need this dark matter halo in order to explain the observations. So what would be the density in this halo in order to explain the observations? And there are many profiles for the density used in the literature, and I think I should mention at least the most famous ones. Suggested dark matter profiles. This means density as a function of radius. Usually one assumes spherical symmetry. Yeah, for the dark matter halo, at the moment, there's no reason to assume that it differs strongly from a spherically symmetric distribution. So it's usually considered to be spherically symmetric. And there are a couple of functions which are used in order to model the dark matter halo, which I think I should mention. In every cosmology lecture, they should be mentioned. The first is the so-called, I do this on the other board, so that I can draw them one underneath the other. So the simplest thing you can imagine is a so-called non-singular isothermal sphere. So you can derive this distribution from an n-body system, of which you assume that it is, it has settled down in a spherically symmetric state, and that it is at a constant temperature. That's why it's called isothermal. Yeah, then it would extend to infinity, and actually you would need an infinite mass, yeah, because it falls off not strongly enough to give you a finite mass. But apart from this, it's nonetheless not a totally unrealistic density profile. And the mu of r is something like mu naught 1 plus r over rho squared. That's mu naught and r naught are constant. Obviously, this has a dimension of a mass density, and this has a dimension of a radius. So there are two parameters which you can match to your data. Yeah? So you observe a certain rotation curve, you assume that there's a dark matter component with this profile, and now you adapt the two constants in a way that your data can be explained with this. And this works not too bad with this very simple model. It works better with another model, which is called, after the authors who found this, the Navarro-Frank-White model. There you have an additional, looks quite similar, but you have an additional r over rho term. 1 plus r over rho squared. This also came out of certain numerical simulations with n-body systems, and it works surprisingly well. It works surprisingly well in order to explain the rotation curves of many galaxies and also of galaxy clusters. So it is used not only for galaxies, but also for galaxy clusters. So this is the most frequently used profile for dark matter density at present. And I should mention at least one additional, there are many of them which have been suggested. There's one by Ernesto, which also works very well. This is mu of r is mu naught, and then the exponential of a function a times r to the alpha. So you have now even three parameters. You have the mu naught, you have the a, and you have the alpha, with which you can play around, and then you can explain the profiles you are seeing. It is common to plot them in a double logarithmic diagram. So what you plot is not r here, but rather the log of r. And what you plot here is not the density, but rather the log of the density. And what you get then is roughly a shape like that. It falls off like that. Yeah? So that's a typical dark matter profile, maybe a little bit flatter. I should more like that. Yeah. So that's a typical density profile in a log-log diagram. And well, if you accept the existence of dark matter, then you can explain all the observations nicely. And you can also explain why galaxy clusters do not fly apart. Yeah, why they are bound systems. Of course, you would like to know what this damn dark matter is, and that's a completely different question. Yes.
Wasn't there also a problem it's called the missing satellite problem?
Well, I'm not saying that. Yes, very good point. What did I say? Did I say you can explain everything with this assumption? Maybe it was not quite clear. You can explain a lot, but not everything. There are simulations with this kind of matter which are used in order to derive the Navarro-Frank-White profile. Yeah, so you have an n-body system of which you make certain assumptions, and then you can not only calculate what kind of spherically symmetric distribution you would get for a stationary galaxy or galaxy cluster. You could also investigate the problem of structure formation of galaxies numerically with this ansatz. And this does not work in all cases. So actually, if you work with the ansatz of Navarro-Frank-White, you get much more dwarf galaxies than you actually observe. So our local group, our own galaxy with its local neighbors, okay, there are a few dwarf galaxies around, but not very many. What these simulations with these dark matter models show is that there should be much, much more. Yeah? Really by an order of magnitude more. And that's one of the problems of dark matter. It's true. So it's not, what I said was maybe a little bit too optimistic. It's not true that you can explain everything with this model, but you can explain a lot. Yeah, this problem of the missing dwarf galaxies is still open, and it's one of the main motivations why some people think in a completely different direction. I will come to that in a minute. Here I'm assuming that the underlying gravitational theory is general relativity, or the Newtonian approximation thereof. You might think about modifying the gravitational theory. You say, no, there's no dark matter. The gravitational interaction is actually described by other equations than what we are using. And that's what some people are trying. I mentioned the best established theories in a minute. But at the moment, let's take the conservative point of view, which is actually the majority point of view. We will not tamper with the gravitational theory. We believe in general relativity. It was so enormously successful. We don't want to change this without really strong evidence against it. So let's stick with that. And then we are forced to introduce this dark matter. And then the question is, what is it? Yeah. Okay, so I said first thing was the velocity distribution, then was rotation curves of galaxies. Now I come to the question, what is it actually? Are there observational data, observational information which could tell us what it is? Well, the first idea is, maybe some of you has got this into his mind, is, well, it's not so unnatural to assume that there's a lot of dark matter in the universe. We know, for instance, that there are black holes. Yeah? We have very good evidence for the existence of black holes. And black holes are certainly dark. Yeah? That's why they are called black holes. Yeah? We may see the matter which is moving around the black hole, but not the black hole itself. So a black hole would be a perfect good candidate for dark matter. And also we know how stars are forming. There are gas balls which are contracting, and if the necessary density is reached, then the nuclear burning will start, and the thing will become a star. But we also know that it's quite frequent that such a dense object is formed, but it's not dense enough in order to become really a star. So maybe the nuclear burning starts a little bit, but then it goes off again, and it doesn't become really a star. So such things are called brown dwarfs. Yeah? So it's a star, a small star. That's why it's called a dwarf, and it's actually not really shining. Yeah, it's burning at a very low level. So like a coal fire which has almost gone out. So we know that such things exist, and also we know that there are planets. Planets, of course, are also dark. So there are plenty of candidates for dark objects. The characteristic similarity between them is that all of them are compact. Yeah, so they are fairly so that the mass is confined into a fairly small region, and then they should produce something which is called microlensing. And microlensing observations give a very strict restriction on the number of these massive compact halo objects, which are abbreviated MACHOs. Yeah? Massive compact halo object is MACHO. So the idea is that this dark matter halo is at least not, there's a certain component in this dark matter halo which consists actually of compact objects. Yeah, not smoothly and uniformly distributed, but rather concentrated in compact masses. And the existence of this thing is strongly restricted by microlensing. So this gives restrictions on the existence of massive compact halo objects. This is MACHOs. So what I already said it. What are candidates for MACHOs? So this is, for instance, black holes. It is brown dwarfs. How is it spelled? In this way? Or with a V? I'm not sure. The singular is with an F, right? Maybe this is with VE. But anyway, you know what I mean. Brown dwarfs and planets. And maybe some other things. So how does this work? What is microlensing? What is one doing? The idea is, if such a thing exists in the halo of our galaxy, yeah, then it should happen with a certain probability that another star moves precisely behind this object. And what happens then? Well, if it is really a compact object, it's not a big object, it is a compact object, then it will focus the light towards us. If it's a big object, then it would just cast a shadow. It would eclipse the star which moves behind it. But if it's a compact object, it would produce a lensing effect. Yeah? It would focus the light towards us. And the light curve which you observe, if you now observe the intensity, the brightness of the star which moves behind the thing, then it comes on, it approaches the line of sight with a certain more or less constant intensity, then it becomes brighter because we have this focusing effect. And then the brightness falls off again. So that's a typical microlensing event. And these events are observed by the thousands since 1990 or so. Yeah, so these big programs searching for such events started around 1990. So there are collaborations where people look for these things in the sky. Actually, there are different directions in which you look. So a large part, actually the largest part, is looking towards the halo of our galaxy. So they are looking for these massive compact halo objects. Another part is where you observe towards the bulge of our galaxy. And a rather small portion of them is about observations in neighboring galaxies. Yeah, in the Magellanic Clouds, in the Andromeda galaxy, not farther away than that. Yeah? If the thing is too far away, then of course these processes are very slow. Yeah? This happens on a time scale of days or weeks. Yeah? So maybe the longest microlensing event for a halo object is something like 100 days or so. Yeah? And the majority is just a few days. So it grows in the course of a few days, and then it falls off, and then it remains constant. And from that, you can actually, the height of this gives you a measure of compactness of the object. Yeah? How much mass must be concentrated in a certain volume. So with the help of these observations, you can estimate the total mass which is in these massive compact halo objects. And the result was that when the first summarizing report on these collaboration was given around 2000 or so, when the first projects have run out, that at most 20% of the dark matter can be explained. Yeah, the dark matter we need in order to explain the rotation curves. Of this dark matter, maybe very generously estimated, maybe 20% can be explained by Machos. So the result of these observations was at most 20% of the dark matter in the galaxy can be Machos. Actually, there was a recent paper a few weeks ago. One of the authors was nobody more, less known than the Nobel Prize winner, Adam Rees. He was one of the persons who did the supernovae 1A observations. So in this paper, with several authors, Rees among them, they brought up the idea again that the dark matter is made out of black holes. Yeah? Actually, this is a very, how should I say, audacious idea, and I think you must be a Nobel Prize winner in order to get something like that being published, yeah? Because most observers would say, no, hey, wait a minute, see, we have ruled this out long ago. Actually, the new idea which came into the play and which triggered this paper was the discovery of gravitational waves. You have all heard about this a couple of months ago. And the gravitational wave signal is explained as an inspiral of two black holes. Two black holes, each with something like 30 solar masses, have come close to each other. They have then merged in an inspiraling process and formed a bigger black hole of approximately 60 solar masses. Not exactly the sum of the two masses of the progenitors, because something like 3 solar masses has been radiated away in the form of gravitational waves within 1 millisecond. Yeah? This is an enormous energy output. Yeah? 3 solar masses in 1 millisecond. This is beyond our imagination. And this, if the interpretation of the signal is correct, and I think there's very good evidence that the LIGO people did a good work, that they really interpreted it correctly, then there are black holes around which are heavier, solar mass black holes, which are heavier than we thought. Yeah? So we distinguish two classes of black holes: the supermassive black holes sitting in the centers of galaxies with millions or billions of solar masses, and the stellar mass black holes. And until recently, one thought that they might have maybe 20 solar masses, but not much more than that. Now we know there is at least one thing with 60 solar masses. And if black holes in this range, say between 20 and 100 solar masses, are more abundant than we had thought, then they could be, that's the idea of the paper, they could be candidates for the dark matter. Actually, they give some arguments why the microlensing observations would not observe these things, why the microlensing observations do not put bounds on the existence of black holes in this mass range. They say, okay, they limit the black holes of less than 20 solar masses, but not beyond 20 solar masses. To be honest, I'm not quite sure if this is true. And I'm really waiting on responses from the people who actually have been doing the microlensing observations. I would think that this idea is ruled out, but okay, it's in the discussion now since a couple of weeks. So the paper appeared in Physical Review Letters a few weeks ago, and there's now a lot of discussions going on. As I said, if you are a Nobel Prize winner, you can afford such a highly speculative idea. Okay. But the standard assumption is that this cannot explain all the dark matter in the universe, that we need something else. And then, of course, the question is, what is it? This is not told us by the microlensing observation. They just tell us what it is not. And there's another type of observations also related to lensing. This is called weak lensing. Well, what is weak lensing? So this is at the scale of our galaxy. Yeah, so we observe compact objects in our galaxy or near our galaxy, maybe in the Andromeda galaxy, but not farther away from that. Weak lensing is something which refers to galaxies far away from our own galaxy. Yeah? And what you observe is actually the deformation effect of intervening masses on the shape of a galaxy. So I think you have all heard about an Einstein ring, what an Einstein ring is. Yeah? So if you have a mass here, and let's assume for the sake of argument that the whole situation is completely rotationally symmetric around this axis. If you have a light source here and an observer here, then the light which comes from the light source to the observer is bent by this mass, so it is deflected. And if the situation is really completely rotationally symmetric, then you should have not only one light ray, but a one-parameter family of light ray, actually a circle's worth of light rays. And what the observer here in this position sees in the sky is the mass, and around the mass, the light source distributed over a ring, which is called an Einstein ring. Now, if the situation is not perfectly symmetric, so if the light source is a little bit off-axis, or if the mass is not completely symmetric, so you have here a mass maybe not completely symmetric, and maybe the light source a little bit off-axis, then you will no longer have the symmetry. You have light rays going here and light rays going here, but they will not form this perfectly symmetric image. So what you would see is, if this is an extended light source, so it has a certain extension, then what you would see is maybe arcs, several arcs, something like that. Yeah. And here in the middle, the deflector. And in principle, such a deformation occurs whenever there is a mass, even if it's comparatively small, so that it deforms the light rays only a little bit. There will always be a slight deformation which has a tendency to stretch the thing in the azimuthal direction. Yeah? So if the mass is sitting here in the center, then it would stretch the images in the azimuthal direction. So in the radial direction, they will appear in the sky smaller than in the azimuthal direction in comparison to the true shape. So this means if you have a large number of background galaxies in the sky, and the mass, distribution of mass between us and these galaxies, you would see all the background galaxies deformed in a little bit. Now, it's very difficult to say in which form they are deformed because we don't know their true form, their intrinsic structure. Let's assume for a moment that we would have galaxies, background galaxies, which are perfectly spherically symmetric. Unfortunately, they aren't. But let's assume they are perfect spheres. Then you would see, without lensing, you would see a lot of circles in the sky. And now if we have lensing, if there are masses between us and these sources, and these light sources, then they would be deformed in this way. Yeah? And the tendency is always to stretch in the azimuthal direction. So here are the sources. Then we would get a shape of this sort. And from this deformation, we could deduce, here's a mass which deforms all these galaxies, if the true shape of the galaxies would be spherical. Now, unfortunately, already the intrinsic shape of the galaxy is roughly elliptical. Yeah? So galaxies in the sky, they have roughly an elliptic shape. So how should we know, how should we distinguish the true shape of the galaxy from the effect of the lensing? Well, this can be done with statistical methods. And the idea is that, okay, the galaxies are elliptical, all right, but the distribution of the axis is purely random. There's no preferred direction. So for purely random distribution of the background galaxies, we can still deduce with statistical methods the mass which lies between us and these background sources just from observing the shape. So what astronomers are doing is they're observing background galaxies in a field in the sky, so they look towards a galaxy cluster. And in the galaxy clusters, in the same field, you also see background galaxies. And actually, a good candidate for a background galaxy is a blue galaxy, because you see it at a larger distance than the other galaxies. So they search in particular for blue galaxies in the field. And then they evaluate their shapes, the distribution of the axis and the eccentricities. And with a very complicated statistical program, actually I've once tried to go through this program. I gave it up after a while because it's awfully complicated. With a very sophisticated statistical program, you can deduce the mass which lies between us and these background galaxies. Actually, you cannot find the spatial distribution, really the distribution in 3 space. What you can get is only the projection onto a plane perpendicular to the view of line. Yeah, so you get a surface mass density, not a density over volume. A density in the sense of mass per area, not mass per volume, only projected into the plane perpendicular to us. And that's what one calls the weak lensing formalism. So weak lensing allows to find surface mass densities of clusters of galaxies by observing the shape of background galaxies. The shapes of background galaxies. And similarly to the microlensing stuff, this has been done since around the 80s or so. Actually, it started a little bit earlier than the microlensing stuff already. So this was done since the 80s or so. So the person who developed this code and this numerical evaluation is an American astronomer by the name of Tony Tyson. And this was then further done by large collaborations of astronomers. So we know, with the help of this method, the mass distribution, the surface mass distribution for a large number of galaxy clusters. And the interesting thing is, there are a few galaxy clusters, a few situations where two clusters meet each other, where they merge or even rather dramatically collide. The best known example of this kind is called the bullet cluster. Maybe you have seen pictures of that. Next time, actually, I will try to show pictures here of the things I'm now talking about when I talk about lensing. So the bullet clusters, actually, one should say, these are two clusters which are colliding. And and this has been done in particular for this pair of clusters. So important example, most important example, actually, in view of dark matter, is the so-called bullet cluster. Well, actually, I should say the first bullet cluster, because by now we have, I think, 3 or 4 such examples. But the first one was discovered in, 2004 or something like that. It is the most famous bullet cluster. So what do you see? You observe, and I will show you pictures last time. I hope I can manage to project pictures in this room. So you will see you see galaxy clusters with this, they become. So one has a center in this area, and there's another cluster which has a center very visible in optical telescope photographs, in particular with the Hubble Space Telescopes in the other area. And then the same field has been observed with an X-ray telescope. So that's what you see with an ordinary telescope. Yeah, just many galaxies here, many galaxies there, and background galaxies. And then you observe with an X-ray telescope, and you see an X-ray, a region emitting X-ray here, which has really the shape of a bullet, which rushes into some kind of matter. And this gave the name bullet cluster to the whole thing. And a similar cloud, not quite so strong with a bullet shape around here. So these here are the galaxies. So the galaxies, and what we see is mainly the light coming from the stars in the galaxies. So this here is what we see in the X-ray. What do we see in the X-ray? Mainly it's hot gases. Yeah? Gases which are moving rapidly and which are very hot. So that's what we see here. Okay. And now you do this evaluation for this bullet cluster. So you see where the gravitating mass is. Yeah? What influences the lensing is any kind of mass. It is dark matter or shining matter, no difference. As long as it is gravitating, it will enter into this gravitational lensing observation. And what you would expect, because in the galaxy cluster, the biggest portion of the mass is in the hot gases, you would expect that the gravitating matter is also concentrated there where the hot gases are. But you see something completely different. You see it's approximately here. So if you calculate where the center of the masses are, you find this here. So this here is the gravitating mass. And if you look at this picture, you cannot avoid the idea that what you see is the following. The two clusters have collided. The stars in the galaxies, there's large spaces between stars. So the stars collide only very rarely. So they go through each other more or less without seeing each other. The hot gases, of course, they feel a strong friction. So they really collide. That's why we see this bullet shape here. They collide and they exert a friction onto each other. And this breaks them. They become slower. They stay behind. That's what we see. Yeah? The galaxies are already here, but the X-rays, what we see in the X-rays, the hot gases, they stay behind. So they have collided, and then the clusters have moved further on, but the gas couldn't follow. The gas stays behind. But then there must be a mysterious component, which actually is a majority of the gravitating mass, which is not the hot gas, which has also gone through each other almost without interacting. Yeah? And this is the most striking evidence for the existence of dark matter I have ever seen. Yeah? So when this picture came out, how would you like to interpret these clouds? If you accept the standard gravitational theory, yeah, so that the lensing calculation is really based on a true on a theory which is realized in nature, how should you interpret this in a different way rather than assuming that a big portion, actually the majority of matter, is dark in the universe? And this is what these clouds produces. And actually this is, as I said, in my view, the strongest evidence for the existence of dark matter. And you have to work really hard in order to do something else, in order to explain this in a different way. Actually, there are people who try to explain this in a different way. As I said, they modify the gravitational theory. Yeah? And I will talk, okay, time is out, but I will briefly talk about this in the beginning of the next lecture. So the most important and most frequently quoted alternative theory is the so-called Mond theory. It has nothing to do with the German word Mond. It stands for modified Newtonian dynamics. Yeah? And the Mond theory is a theory which was invented in order to explain the rotation curve, and it works fine for that. Yeah, so they just modified the gravitational law in a way that they could explain the rotation curves without dark matter. But Mond completely failed in the explanation of the bullet cluster. Yeah, the inventor of Mond was is an Israeli astronomer by the name of Milgrom, and he admitted that he cannot explain the bullet cluster within his theory. So he can explain part of the dark matter, but not everything which can be seen. So in my view, Mond is dead now, but this is a personal view. Yeah? So I will mention these alternative theories next time. And I will also then list a few of the speculations what the dark matter could be. But I will already give away the punchline of this section. What we will take away from this is that when we do cosmological models, we have to take this dark matter into account. So the matter is not just the matter which we see in the galaxies. There's a strong dark component. And what we model as matter, as a dust in the universe, is to the larger part actually this dark matter. So that's what we will take away from this section. And we have to keep this in mind when we then form our cosmological models. Okay, I continue with that on Tuesday. See you on Tuesday.